I'm Mark Richardson, a research engineer at Facebook Reality Labs, and I'll be discussing work from myself, Matt Durasoff, and Robert Wong on decoding surface touch typing from hand tracking. In virtual and augmented reality, text input is important for communication and productivity. Here we investigate the use of hand tracking to enable touch typing on a flat surface. There already exists a wide audience of effective typists, and this could allow them to transfer their skills into AR and VR. We've seen from recent consumer devices that hand tracking can be achieved through on-headset sensors without extra peripherals, potentially making this suitable for on-the-go use cases. Our investigation caters particularly to the fastest typists, touch typists. Without the feel of physical keys and without using sight to find keys, fingers will drift during typing. Instead of requiring users to make precise contacts on a fixed keyboard layout, we investigate using a motion model to recognize finger trajectories. Here we sidestep the current limitations of consumer head-mounted hand trackers by using a high-quality marker-based hand tracking system. While this introduces a gap in tracking quality compared to what's achievable on AR and VR headsets, we can study the potential of hand tracking applied to this problem. This problem is analogous to speech recognition, so our system design follows the design of modern end-to-end speech systems. For every frame of hand data, our motion model predicts a distribution over the set of keys pressed at that frame. We use a neural network to represent our language model prior, which provides a probability distribution over character sequences. A beam search decoder combines the character heat map sequence with our language model prior to predict the text that was typed. To train our motion model, we need a ground truth dataset. We recruited 20 self-identified touch typists who we prompted with specific short phrases and recorded their hand motion as they typed on a paper keyboard. Participants also typed a set of phrases on a physical keyboard to establish a performance baseline. With this data, we compared throughput across modalities and found no significant difference in typing speed between physical keyboards and flat surfaces, so it seems that touch typists are able to transfer their skills to typing on surfaces. Compared to typing on a physical keyboard, our surface touch typing system was nearly as accurate with a mean uncorrected error rate of 2.7%. While it looks like people might still type on keyboards more accurately than on surfaces, the difference isn't statistically significant. Typing on a flat surface isn't a new idea. Soft keyboards are pervasive on our phones and tablets. One question we had was if hand motion was fundamentally more informative than contact. To better understand the performance of our approach, we decided to compare against methods that decode ground truth contact events from a touchpad. To do this, we placed a pressure-sensitive touchpad underneath the paper keyboard so we could evaluate our motion model against contact decoding baselines. For decoding 2D contacts to text, a method was proposed by Goodman et al. In 2002. Given a set of 2D contacts per key, we can fit a bivariate Gaussian per key. Then a novel 2D contact can be evaluated according to each Gaussian to get a distribution over the set of keys. This simple approach can achieve a mean UER of 5.7%, but we found that our approach outperformed it at 2.7%. We posited three key factors that account for the delta. The first factor is that our motion model can leverage finger identity information while the contact method cannot. Here, for three different participants, we've plotted their fitted Gaussian models, and we've colored each Gaussian by which finger typically hits that key. In general, we found most typists have reliable correspondences between specific fingers and specific keys. To somewhat quantify the value that finger identity adds, we tried a modification of the Gaussian approach where for every contact, we used hand tracking to find the finger responsible, and then we fit one Gaussian per key per finger for each user. With finger identity, the mean UER of the contact approach improves from 5.7 to 4.8%, better but still short of our motion model. The second factor is that our motion model makes one prediction every 60th of a second, while contact methods make predictions only when a contact occurs. The contact method predicts one key for every contact, so missing or spurious contacts automatically mean incorrect decodings. On the other hand, out of necessity, our method is able to predict the possibility that no key was pressed, allowing for event insertion or removal according to the language model prior. Here, for example, it can predict a weakly predicted H that has no contact event to spell the word with. The contact method can't recover from this. To quantify this effect, we evaluated both approaches after filtering out all samples with these artifacts. This is an easier dataset, so both contact and hand motion decoding perform better. The gap between contact and hand decoding narrows from 2.1% to 1.6% though, suggesting that continuous motion decoding is responsible for some of the accuracy gap. But still, there's this 1.6% gap that's left. Where does this come from? We think the third factor is that our approach is able to leverage 3D trajectories instead of only 2D contact points. Here you can see two clusters of trajectories of all the times one user hit the I key and the O key. In green, you can see a novel trajectory which lands on the I key among all the blue trajectories, but the shape of the arc is undeniably similar to some red trajectories. While the contact method can only see the 2D contact, our motion model can see the shape as a whole and can correctly classify this case. Finally, we enabled this end-to-end system, including motion model and beam search decoder with language model prior to run in real time at 120 Hz on a desktop GPU. We created a toy text entry application with an Oculus Rift and the Unity game engine to demonstrate real-time touch typing on a flat surface in VR.